Okay, to kick off the afternoon here, we are going to talk about individual testing. And I don't know about you all, but that morning was pretty fascinating. Did you like it? Yeah. I mean, we hit a lot of areas there. And I just had a quick discussion with Mike Snyder about an element that I think a lot about, which is, does everybody actually want to know about this stuff? Did he really want to know? I mean, we talked about his brush with Lyme disease. It might have just been dismissed as, kind of an odd something. He got sick. It wasn't severe Lyme disease, and he found out it could be a very serious disease. And do you want to know? Which I think is something that we can think about, as we're contemplating all of this. So I'm going to tee up this panel with a few thoughts, and it's kind of a retrospective. Those of you who know me, a little bit about my experimental man project, where I went out and basically took every test possible, although not nearly as many as Mike. I don't have as many toys as he does at Stanford. But especially, I've been taking these tests for about 15 years. And the original testing was I was one of the first people to ever be genetically sequenced way back in 2001 for a Wired story. And I didn't even know what I was doing at the time. I just moved into covering this area. And I didn't realize that I was one of the first people, and that was kind of an interesting thing to do at the time. And this is way before 23andMe and even Illumina or a lot of the technologies that we have now. So I'm going to share with you a little bit about that, kind of a personal perspective, and then we're going to have an amazing panel here that's going to tell us about some of their thoughts and research and interests around this idea of individual testing. So I'm going to tell you a little bit about you as data, and you, me. I mean, a lot of this is about me, but it's really about all of us. And this is my family, or at least part of them. It could be your family. But as we're, you all are academics, as we're getting all academic here, let's remember that this really is about real people. And so this is what we look like on the outside. And this is what we look like, or one version on the inside. And I borrowed this slide from Eric Schatt at Mount Sinai. And this really just gets to the beginning of all the possibilities. But these are all the various networks, organs, et cetera, that bring in data. And we've heard that mentioned over and over again today. And I give a whole talk called Biobabble, Too Much Data, Too Little Understanding. And we're, I think, up to 6 or 7 zettabytes of data in the world right now. And this is almost doubled in the last couple of years, and we're on an exponential curve on that. That's all data, not just health data. But to me, as a person that has all this data, we need to figure out how to rein this in, which I'm going to talk about a little bit here. So just to reiterate the Experimental Man Project, I now am up to, actually it's almost 70,000 genotypes annotated. And I'm on a program that automatically just collects, I have bots swirling around collecting information on new markers as they come available in studies. So I have to just check it every so often. I can tell you, though, that the 60,000 plus genotypes annotated have not really been very significant to me. So as a healthy person, I come from a pretty long-lived family. We're very lucky. There have been some, but mostly not. I have had over 1,000 environmental levels, toxin levels taken inside my body. And this started with a National Geographic story about 10 years ago called The Pollution Within. And some of you, at least a couple of you actually, I think, worked with me on that story, where I went out, good experimental man style, and had, I think it was, that was about 400 different toxins. And we went all over the country trying to figure out, like National Geographic does, where I might have been exposed to these very tiny, minute amounts of things like pesticides and metals, et cetera. And I discovered a couple of things, like I actually grew up in a pretty nice neighborhood, but it wasn't too far from a toxic waste dump that ended up being one of the largest Superfund sites in the country in Kansas. And I had trace amounts of some of those chemicals. Again, these are one of the things we don't understand about these chemicals is these tiny trace amounts. What does it really mean? Parts per billion, parts per trillion. We all carry them. Lots of time in an MRI scanner, all the omics that Mike talked about, although, again, he's done much more than I have. More recently, way too many wearables and apps, most of which doesn't produce information that's very interesting to me. And the costs of this, when I did a lot of this research a few years back, it was around 150K. It's probably less than 20K now, which is interesting. And that was mostly sequencing that cost 6 years ago or whatever it was, 8 years ago. And obviously, this is really big data. When we talk about big data, I've got, actually, it's closer to 15 terabytes of data now. Again, the data just keeps accumulating. And if everybody on the planet had this much data, we would be in yottabytes of data, which is 10 to the 24th. I still, maybe one of you all can help me. I ask literally thousands of people, where does Yoda, where did that come from? It's not Yoda like in Star Wars, Yota. I mean, and by the way, after this, we don't have a name for bigger numbers than this. But since we're already in that realm, if everyone had the amount of data that I have, we probably need to start thinking about new names for numbers. So give you just a quick run through of some of my data, and I'm not going to really spend a lot of time on this because I don't have much time. But I have data like I have a 50% increased risk factor for a brain aneurysm. Okay, that sounds slightly scary. This is 23andMe style data, GWAS data, although they can't, 23andMe now can't use it anymore, according to the FDA. All that means is that I actuarially have about a 1 in 200,000 chance of having a brain aneurysm. And this gives me 1.5 in 200,000. So while to a layperson that doesn't really exactly understand probabilities or risk factors, that sounds a little scary, it actually is almost meaningless. So that's interesting. And much of this data for common diseases on genome-wide association study data, which is most of our data, has kind of similar low effect sizes. Warfarin sensitivity, pharmacogenomics, this is more interesting. There's a lot of interesting things happening with this. I'm a hypermetabolizer of the blood thinner warfarin. This is one I actually would like to have tattooed on my body if I was unconscious, in case they gave me the normal dose. I always love, there are all these behavioral, I don't know if this is being done so much anymore, but I am high risk for low empathy. But as I always say, I don't care what you think. And then the toxin levels, I have a 50% higher. Now this is levels now, actual amounts, not probabilities. I have a 50% higher level than the CDC mean for DDT or DDE, the metabolite it breaks down into. It's probably because I grew up in eastern Kansas where they were spraying this stuff. I'll talk about mercury in a second. And then MRI scans, I have no trace of Alzheimer's, or at least I didn't a few years back. You can actually get a decent predictive capability using a very expensive process of brain scans. And then again, behavioral MRI scans, functional MRIs, I have normal greed. Not sure what that means. Way open to interpretation. I'm going to just throw some stuff at you here because I really just have a few minutes here. This is the kind of data that one gets when they're doing this massive sort of self-testing. And by the way, I didn't do this because I actually am even that interested in it, personally. Again, I come from a fairly healthy family. I tend to be fairly fatalistic about things like this, but as a storyteller. So that's what our theme is for the entire meeting. Really, as a communicator, this is a way for me to test drive all these technologies. But this is the kind of data that I got on heart attack risk. This is a mix of traditional tests and more high-tech tests. The bottom line is that I had a 2% risk factor for heart attack in 10 years, my Framingham score, which looked like it was nothing. However, when I ran all this data through an algorithm with a company called Intellos, and actually had it backed up a couple of years ago with another company, I have a very high risk factor for heart attack, according to but only if I gain a pound a year in weight. So if I keep a steady weight according to this algorithm, and this is all based on genetics and metabolites, or my metabolic profile, if I keep a steady weight, I'm okay. If I don't, I'm not. So these are the kind of choices that we would like to be able to have this data produced for us, although that's very preliminary, and I have a lot of people that have criticized how that was put together. But my favorite genetic marker, caffeine fast metabolizer gene. How many of you all can drink coffee right before you go to sleep and still go to sleep? Okay, it's about 25% of the population. And since I love coffee, I'm very happy about that. So I have a bunch of data, Fitbit stuff, which, again, we were talking about that at lunch. As far as I can tell, research at UCSF helped me with this. The 10,000 steps is totally made up. There's no research at all behind it. And I got a little frowny face there because I didn't do it, which I guess, motivated me the next week to, do twice that. Now we get into the personal environmental report card and testing, and this is from that National Geographic story. Again, I have a lot more data since then, but this gives you the sort of idea of the level of testing, if one really wants to do it. And Geographic spent, I think, about $15,000 on this. A lot of it we got done pro bono. I'm not sure those prices have gone down much, so the average individual is not going to be able to do that. I'm going to deep dive here just for a second into kind of an interesting line of research that I've been developing here on environment and genes. And we do need to take that picture of the inside of us and put it back together again, in the system. So combining these two is really important. You get mercury from eating big fish or amalgam fillings and lots of other ways. This is my personal testing for a number of the genes associated with risk factors for mercury exposure. It's everything from asthma to probably more seriously cognition, mood, things like that, neural deficits. And I got involved with something called MercuryWise, and it's a company, although the company is kind of in stasis right now. But we put together a research team that did a lot of interesting work on this idea of combining genes and a toxin like mercury. And we piggybacked onto an NIH-funded longitudinal study that was published in JAMA. And this might be a way to actually tie together genes and at least environmental toxins, because there's a wealth of information out there in toxicology on the impact of toxins on different diseases and phenotypes. So the original study without genetics came out with the two arms of the study. One group of children were given amalgam fillings with mercury, the other were not. And they came out almost identical. It looked like amalgam fillings weren't that dangerous, even though they're half mercury. When we added genetics, though, we got a very different assessment. In fact, about 1 out of 5 of these kids had a risk factor of 3 to 6 year developmental delay on standard neurobehavioral testing, and pretty high standard deviation, about 1.6 standard deviations and great p-values and all of this. And so these are the genes that we tested. And it's also actionable because you can actually find ways to avoid mercury, like don't eat big fish. From a communication standpoint, we've been working very hard on how to communicate this, working through the regulatory pathways. It's been a very interesting journey, which I can't get into in any detail here. But these are some of the ways that we put together reports. And then just to conclude here with a few ideas to kind of tee us up for the panel, about 99% of my data is not useful yet. Maybe 98, okay, a little bit squeaking in there. And this really tells us something, at least an individual trying to figure this out. And I think we have some of these protocols that you all are talking about up here, which are, very complex, and then a guy trying to do it down here, and these need to attach themselves. And anyway, data does not mean understanding, as I said a minute ago. We need to really bash the silos. I'm even seeing some of that here. I mean, we need to step out. Specialists need to talk to other specialists. We need to talk to people, and as I mentioned, emotions. Massive efforts at these holistic efforts, ecosystems. And then AI in health, which is actually what I'm working on right now. This is how we can probably bring a lot of this together, but we need to build the infrastructure to bring all this data together. Resets and policy and everything else. And then I would love to have you all let me know what you're up to, because I'm doing a second phase of the project, which is about trying to understand all this data. So thank you. I will move over here. My name's right here, so I'll stay here. Hi. So why don't we just move down our table of panels there. Phil, do you want to introduce yourself and tell us a little bit about what you're up to?
Hi, I'm Phil Brown. I'm at Northeastern University. I'm director of a center called SERI, the Social Science and Environmental Health Research Institute, and we have lots of collaborations between environmental health scientists, sociologists, anthropologists, and science and technology studies people. And what I want to just say a few words about is the question of reporting back data to participants in environmental health studies, which is work I've been doing for quite a while. This is to advance it.
Yeah, It's up.
So